Good morning, children. Stay safely at home. So, I am starting the next chapter, Electromagnetic Induction. Now, before knowing the term about the term electromagnetic induction, we have to know about the magnetic flux. Alright. So, we have studied already about the electric flux exactly in the same manner. One can explain what is magnetic flux. Okay. What is magnetic flux? This is the amount of a total number of magnetic lines of forces crossing any area perpendicularly is known as the magnetic flux linked with that particular area. Now, we have the concept of magnetic field intensity also. What is magnetic field intensity? The number of lines of forces crossing unit area perpendicularly. So, if you consider this one, that here you see how the lines of forces are going perpendicular to the area taken. Alright. So, you see the magnetic field intensity, if it is B, magnetic field intensity gives you the number of lines of force crossing unit area perpendicularly. So, if you consider the entire area of the surface is A, then if you multiply B with A, that will give you the total number of lines of forces crossing the entire area perpendicularly. Okay. So, one can write magnetic flux is equal to B into A. Alright. Now, in this case, what we have considered, that lines of forces are perpendicular to it. Means if this is the area, then lines of forces are like this. Okay. But it may not be like that always. Now, if you consider this case, that lines of forces, just you consider this is the palm and this is the surface through which the magnetic lines of forces are crossing. But suppose the lines of forces are crossing like this. Okay, the pen is the lines of force. Then you see this is the lines of force. Then you see these lines of forces are not perpendicular to the surface. Alright. Now, if you consider the area vector is along this direction, isn't it? I hope you can remember the concept of the area vector. Area vector is always perpendicular to the surface drawn. So, you see if this is the area vector and this is the magnetic lines of force, if the angle between them is theta, then if you take component B cos theta, that B cos theta will be along the direction of A. Alright, so B cos theta gives you the number of lines of forces crossing unit area perpendicularly. So what will be the total number of lines of forces crossing the entire area? It should be B cos theta into A. So you can write it as BA cos theta. Alright, now you know that magnetic field intensity, this is also known as magnetic field induction. And B and A, both of them are vectors. So, one can write it as magnetic flux is B dot A. We have written no electric flux. Before discussing the Gauss's theorem chapter, electric flux concept already you have got. There you can remember phi E. It was written as E dot A. So, like that, magnetic flux density, it is given by dot product of magnetic field intensity and the area vector. And when the magnetic lines of forces or magnetic field intensity perpendicular to the surface itself, is that clear? Then theta becomes 0 and cos 0 is 1. In that case, what will be the magnetic flux? Simply the product of magnetic field intensity and the area vector will give you the amount of magnetic flux. Now, SI unit of magnetic flux is Weber. Okay, after the name of one physicist. That's why when you are writing the full form, it should be W small, and in short form, it should be W capital, but you have to write B also. Why? Because I hope you can remember that SI unit of power is watt. So, in that case also we use W. So, just to differentiate between watt and Weber, we use the W capital and then small b. Alright. Now, you know that magnetic flux is equal to B into A. So, you see the B, magnetic field induction or magnetic field intensity, two name I said of B. B is magnetic field induction or magnetic field intensity. Okay. So, you can write B is equal to phi by A. Alright, so you see, if you consider phi is Weber, A is meter square, so instead of writing Tesla, one can write the unit of B also as Weber per meter square. I hope you can remember that we can write Weber per meter square or Tesla. Then as B is equal to phi by A, that's why B has another name. What is the name of B? That is magnetic flux density. Alright. So B, I have said three names. What are the names? Magnetic field intensity, magnetic field induction, or you can say as in terms of magnetic flux density. Okay. Now the question is, what is the dimension of phi? How you can get it? Phi is equal to B into A. Alright, again you know that force acting on a current carrying conductor placed in a magnetic field is given by F is equal to ILB. So B is how much? F by IL. So if you put that, you are getting FA by IL. Now you put the dimension of F, mLT to the power minus 2. A is the area, L square, I is current A, then L is length L. So on simplifying it, what are you getting? Dimension of phi is ml square t to the power minus 2 a to the power minus 1, same just like the electric flux. Okay, electric flux and magnetic flux, if you consider, both are having the same dimension. Now I am coming to the original term, that what is electromagnetic induction. Alright, we can understand it from this very simple experiment. So what we have taken? Just see, we have taken different turns of a coil and the two ends of the coil connected with a galvanometer. Alright. So you see, in this closed circuit, there is no source of current. So what will happen to the galvanometer? Galvanometer pointer will be at 0 and it will not deflect. Why? Because there is no source of current in this circuit. So the galvanometer is not deflecting. Alright. Now you do this. Suppose you have taken north pole of a magnet and you bring the north pole of a magnet very first towards the coil. Then you will observe that current will flow in the coil in this way. You see, the current is flowing in this direction and the galvanometer will deflect towards this direction. Just you see, if the current flows in this direction, means what? The current will come out and the galvanometer will deflect from left to right. Alright, another thing, when the north pole is in motion, then only galvanometer will deflect. When the north pole will stop moving, then what will happen? Galvanometer will not deflect. And what is said? Galvanometer will deflect towards right. Okay. Now, if you do this, now instead of bringing the north pole towards the coil, if you take the north pole away from the coil, then also you will see, till the north pole is in motion, moving away from the coil, galvanometer will deflect, means a current is passing through the coil, passing through the closed circuit, and in this case the galvanometer will deflect towards the left, means right to left the galvanometer will deflect. Alright, now why it is happening? Okay, because when the north pole is in motion, then what is happening? Magnetic flux linked with the closed circuit or magnetic flux linked with the coil changes. So when the magnetic flux linked with the coil changes, an EMF will be induced in the coil, and if the circuit is closed, then a current will flow through the circuit. So this phenomena is known as electromagnetic induction. I repeat, when the magnetic flux linked with the coil changes, then an EMF will be induced in the coil, and if the circuit is closed, then a current will pass through the circuit. This phenomena is known as electromagnetic induction. Why the term electromagnetic coming? Change in magnetic flux causing a development of or production of an electric EMF. Alright, so it is known as electromagnetic induction. Alright, and the current and this one, when you are considering the current passing through it, this is known as this one current is known as the electromagnetic current. The phenomena is known as the electromagnetic induction. Alright, now Why the flux is changing? I hope you have understood. Just you consider this. If you consider the North Pole, then you see from the North Pole, this is the way the lines of forces are coming out, isn't it? So if you take the coil near the North Pole, then more number of lines of force will cross through it. And when you are taking the area here, you see then what will happen? Less number of lines of force will cross through the area. So when the North Pole is in motion, then what is happening? The magnetic flux linked with the coil is changing with time, and due to this an EMF is induced and a current passes through that current is also known as induced current or electromagnetic. Induced current is better to say. That current is known as the induced current, and the phenomena is known as the electromagnetic induction. Now when the electromagnetic induction takes place, then it always obeys two laws. That laws are known as the Faraday's laws, as Faraday first gave that law. That's why it is known as Faraday's law of electromagnetic induction. Now what is the first law of electromagnetic induction? First law of electromagnetic induction, already you studied in 10th standard. 10th standard, you studied two Faraday's laws of induction, isn't it? I hope you can remember. The first law was that when there is a change in magnetic flux linked with the coil, then an EMF will be induced in the coil, and the EMF will last as long as there is a change in magnetic flux, isn't it? That was the first law you studied. And second law you studied as the magnitude of the EMF induced in the coil is equal to or proportional to rate of change of magnetic flux induced in it. Okay, EMF induced is directly proportional to rate of change of magnetic flux linked with it. These were the two laws, isn't it? Now here what is done, that both the laws are combined together and given as the first law of electromagnetic induction. It is also known as Faraday's law and also known as Newman's law. This is the new concept you are getting. Faraday's first law, or also known as Newman's law. Okay, and both the statement, now it is combined and it is given as when the magnetic flux through a circuit is changing, an induced EMF is set up in the circuit whose magnitude is equal to negative rate of change of magnetic flux, means phi is given by minus d phi b dt. And already you know that this negative sign, actually it is coming from the third law, that is known as the Lenz's law. Here we will call it as the second law of electromagnetic induction. Alright, so you must learn the statement of the first law of electromagnetic induction and also the mathematical representation of the first law. This is the mathematical representation, that magnetic flux is equal to minus d phi b dt. Induced EMF. I'm really sorry. Induced EMF is equal to minus d phi b dt. Induced EMF is always equal to negative rate of change of magnetic flux linked with the coil. And this first law, the another name is Newman's law. That also you must remember. Now in the earlier discussion, we have written E is equal to minus d phi b dt. Then we have considered that there is only one turn. Okay. But if there are n number of turns of the coil, then you see what will be the total magnetic flux linked with the coil. With each turn it is phi b. So with n number of turns, total magnetic flux will be n phi b. So E will become equal to minus d n phi b dt. Alright. And now this n phi b, what is its name? It is known as number of magnetic flux linkages in the coil, and its unit is Weber turns. Okay, phi is Weber, n is turns. Okay, although you have written n phi b, but what is its unit? We generally use the unit Weber turns. So these are the few, means 1 mark important conceptual points you must learn and remember for your exam. Now the second law of electromagnetic induction is that direction of the induced EMF or the current in any circuit should be such that to oppose its cause. Alright, so let us understand it. Just you consider here when I have drawn the previous diagram. I hope you can remember it, that the galvanometer is here and you are bringing the north pole towards it. Then I said that the current is in this direction. Alright, in the anti-clockwise direction. Clear? Now how I have told you that it is in the anti-clockwise direction? Because mentally I applied the Lenge's rule and then I said the direction will be in the opposite direction. Okay. So let us apply this Lenge's law here. So you see what is said, that direction of the current should be such that it is oppose the cause that produce it. So here you see what is the cause. Why the current is induced? North pole is coming towards it. Alright, so what it will do? It will oppose the means coming of north pole towards it. So how it can oppose? So that the current direction should be such that a north pole should develop in it. Alright, in 10th standard already I taught you this topic. So here north pole means you know that in a coil when the current flows in the anti-clockwise direction, then north pole will be induced. You see here when the current will move in the anti-clockwise direction, north pole will be induced and this north pole will oppose the movement of the north pole towards it. Alright, so you see what is happening. The direction of the induced current you can get by applying the Lenge's rule or the second law of electromagnetic induction. Second law of electromagnetic induction, also known as Lenge's law, L-E-N-Z, that is Z written, L-E-N-Z, Lenge's law. Okay, so Lenge's law gives us the direction of the induced current or EMF, and in that one E is equal to minus d phi be written. Why the negative sign written? Negative sign indicates that one, that it should, induced EMF should be such that it should oppose the cause. That's why the negative sign was there. Alright, so actually in the first law E is equal to minus d phi b dt, that minus sign is coming due to the second law. So you must learn both the statement of the first and second law of the electromagnetic induction. Now instead of applying the Lenge's law or second law of electromagnetic induction, if you want to find out the direction of the induced current, then you can use another rule, that is Fleming's right hand rule. This is nothing new I am teaching to you, because in 10th standard before alternating current generator you studied this. Alright, so what is Fleming's right hand rule? I hope you can see that you set the first three fingers of your right hand. First three fingers means the thumb, the first finger and the middle finger perpendicular to each other. Alright, and then you know that the thumb, it gives the direction of motion of the conductor, and the first finger, it gives the direction of the magnetic field, and the middle finger, it gives the direction of the induced current. Again you apply the same rule, that father, mother, child. Alright, father means it is the force, means along the force the conductor will move. So it is the direction of the force, means the direction along which the conductor is moving. Then M stands for mother, M, and here M stands for magnetic field, direction of the magnetic field. Then C, child, direction of the current. Alright, so again the Fleming's right hand rule, it also helps you, or it also gives us the direction of the induced current. So direction of the induced current one can find out either by using Lenge's law or by using Fleming's right hand rule. So from the first law of electromagnetic induction, we have got the magnitude of the induced EMF. So from that one, easily one can find out what will be the expression for induced current and induced charge. Alright. So what will be the induced current according to our concept of current? Current is EMF by resistance. So induced current should be equal to induced EMF by resistance. So if you substitute, what you are getting? Minus N by R d phi b dt. Is that clear? Now then what will be here? You can just neglect the negative term, negative one, because here it is coming due to the fact that current opposes the cause. So negative, if you consider only the magnitude, then negative sign you don't have to write. Negative sign is coming due to the fact that direction of current should be such that it should oppose its cause. Alright, then next one is what will be the amount of the induced charge. Induced charge, you know, charge is given by current multiplied by time. So here we have considered the time as dt, so you can write I dt. So what you are getting N by R d phi b dt into dt. So you are getting N into d phi b by R, means induced charge is equal to number of turns into d phi b is what? Change in magnetic flux divided by resistance. Alright. So if you look at the relation that induced EMF does not depend on resistance, and induced current, it depends on resistance, and induced charge, it also depends on resistance. Okay. So these are the three expressions that I wrote within the rectangle that you must learn and remember for solving. Now in the electromagnetic induction, what we have seen that if you want electromagnetic induction, then magnetic flux you have to change. Alright. So how you can change the magnetic flux? There are three possible ways to change the magnetic flux. Very simple to understand. You know magnetic flux is given by BA cos theta. Alright. So you see you can change phi by changing theta. Alright, so how you can change theta? By rotating the coil, that we have done in which case? Can you remember? In alternating current generator, 10th standard already you have studied. So when you are rotating the coil, then what will happen? Angle between B and M is theta will change. Alright, in that case, how you can write the induced EMF? You see, induced EMF is d phi dt. So you can just write it as d phi d theta into d theta dt. We can do no. We are applying the concept of calculus. So d theta dt is what? Omega. Now you see phi is equal to how much? Phi is BA cos theta. So I am just showing it here. You don't have to write this part. This part you don't have to write. For your understanding I am writing d theta of BA cos theta. Alright. So you see B and A does not depend on theta. So you can take it outside the derivative. So d theta of cos theta, how much? d theta cos theta is minus sin theta, that only written here. And you know d theta dt, it is what it is nothing but the angular velocity of the coil, angular velocity of rotation of the coil, that is omega. So you see it is you are getting minus omega BA and it is coming minus sin theta here. It is coming d theta of cos theta means minus sin theta. So minus minus getting plus. What is the expression for E? Then omega BA sin theta. Alright. Already we have used it in the discussion of alternating current generator. Then next step, that how you can change phi. You can change phi by changing A. Now how you can change the A? Just you consider this. Suppose the magnetic field is in inward direction. Alright. So magnetic field is inward direction and now you consider this pen. If I drag the pen in this direction, then you see when it is fully inside the magnetic field, then magnetic flux is maximum. So the moment I am dragging it in this direction, then you see less number of area now coming under the magnetic field. So what is happening? In this case, when it was here, the pen was here, the magnetic flux was maximum. Okay, now when you are taking it out of the magnetic field, then what is happening? The area that through which the magnetic lines of force are crossing, that is decreasing. So magnetic flux decreasing. Now if you do the opposite thing, that the pen is here and you are dragging it, okay, within the magnetic field, then what will happen? Magnetic flux linked with the area of the pen, it will increase. So you can change by changing theta, by changing A. Then the next one will be by changing the magnetic field intensity B. Next is how, as I said already, that how you can change the magnetic flux by changing B, because you know phi is equal to BA cos theta. Alright. So in that case, what will be the induced EMF? In place of phi, if you write BA cos theta, then A and theta, they are constant, they are not changing. So you can take it outside the derivative and induced EMF will become then minus A cos theta dB dt. So you must remember that we can change the magnetic flux either by changing theta, means by rotating the coil, and in that case what will be E? It will be B omega A sin theta. Alright, and you can change it by changing A, and you can change it by changing the magnetic field B. Alright, so these are the three ways one can change the magnetic flux linked with a closed circuit. So that's all for today. Thank you, girls.